In this video, I'll walk you through an example of how to run the BFS algorithm. Let's get started with the following graph. We'll also need a queue to keep track of the nodes as we visit them. Initially, all the nodes in the graph except the source node are colored white, and the distance from any node on the graph to the source node is infinity. We then color the source node gray and add it to the queue. And we look at the adjacent nodes to the source node. In this case, we have the node R and the node W in the adjacency list of the node S. We color node R and node W gray, and we add them to the queue, and we remove S from the queue. We now look at the nodes that are adjacent to the node W. Because they're white, we color them gray, and we update the color of W to black. Now that we have removed the node W from the queue, the next node in the queue is R. All we have to do is color V gray and update R to black. Then we can remove the node R from the queue and add the node V to the queue. We now look at the node T because it's the first element in the queue. The node T has three adjacent nodes, the node W, the node X, and the node U. But the node U is the only white node, and that's the only node we care about. So we color the node U gray, and we update its distance from the source node. We then add the node U to the queue, update the color of the node T to black, and remove it from the queue. Right now, the first node in the queue is the node X. It has 4 nodes adjacent to it, and they are the node W, T, U, and Y. We're only interested in the white nodes that are in the adjacency list of the node X. And in this case, it's only the node Y. So we'll go ahead and update the color of the node Y to gray, and we'll add it to the queue. We'll then remove the node X from the queue and update its color to black. Although we've visited all the nodes in the graph, we can't stop now because we still have elements in our queue. We have the node V as the first element in the queue, so we check if the node V has any nodes connected to it or adjacent to it, and it doesn't, so we remove it from the queue and update its color to black. And the node U does not have any nodes that are adjacent to it and that are white, so we remove the node U from the queue and update its color to black. Finally, we have the node Y. The node Y does not have any adjacent nodes that are white, so we remove the node Y from the queue and we update its color to black. At this point, the algorithm stops because the queue is empty. The result of running the BFS algorithm is a tree that contains all the nodes that are reachable from the source node and the shortest path of every node from the source node. We can also use the BFS algorithm as a building block for other algorithms and to build a minimum spanning tree for unweighted graphs. Here's a pseudocode for the algorithm. It's essentially the same process that I walked you through with the example. This algorithm enqueues every node at the very most one time and dequeues every node at the very most one time. So it runs linearly to the number of nodes and edges in the graph.